In this video, we're going to look at how glycogen is broken down so it can enter glycolysis. So just a little overview of where we've been so far. So we've looked at how glucose can go to glucose 6-phosphate, how that can go to pyruvate, and then how it can be made into lactase or ethanol off your yeast. We have not talked about the citric acid cycle or how pyruvate is made into amino acids yet. We also talked about how glucose 6-phosphate can go to ribose 5-phosphate through the pentose phosphate pathway. This can go make nucleotides, this can make NADPH, or it can just be recycled back. Now we'll talk about glycogen. Glycogen is the main storage of glucose in your cells, and if you break down glycogen, that can go in and make glucose 6-phosphate, or you can take glucose 6-phosphate and remake glycogen, your storage. So just a refresher of what glycogen is back from Biochemistry 1. It's a polymer that of glucose that is alpha-1,4 linked, and you have alpha-1,6 branch points every 8 to 14 residues. So you have a granule of 11 to 44 angstroms in diameter. They form these giant spheres that contain roughly 120,000 glucose molecules per sphere. Your muscle, 1 to 2% of your weight is made out of glycogen, and your liver, about 10% of your weight is due to glycogen. And when you're removing glucose from glycogen, you can only remove it from the non-reducing ends, which is a good thing. Because if we look at how glycogen is made, all these branch points leave us with all these non-reducing ends, while the start of the glycogen molecule has only one reducing end. So to remove glucose fast, we can remove from all these reducing ends at once all these non-reducing ends at once instead of just the reducing end. So let's take a look at glycolysis, which is glycogen breakdown. And you need 3 enzymes for this. The first enzyme is glycogen phosphorylase, and this will catalyze the glycogen's phosphorylases. So let's look at this. Glycogen is our molecule. Phospho is that molecule, phosphorus. Lysis means cut. So you're breaking a bond by substitution of a phosphate group. And from this, you're going to make glucose 1-phosphate. Our overall mechanism, or reaction rather, is glycogen, certain number of N residues, so this is just any number, plus phosphate will make glycogen, now you're less than 1 residue, plus glucose 1-phosphate. This enzyme will only work on glucose units if it's at least 5 units away from the branch point. So if you're at a branch and you're closer in than 5 molecules to where that branch starts, you cannot be cut off by this enzyme. It can only work for glucose further than 5. And that has to do with how this enzyme interacts with your molecule. The binding pocket will only accept 5 glucoses for the 5 glucoses. So if you're shorter than that, the enzyme won't bind. So if after we chop off like a branch and we get down to the last 4 glucose molecules, the next enzyme that's going to be used is glycogen debranching enzyme, which will remove our branches that we cannot get to with glycogen phosphorylase, and we're just going to rearrange our branches to make these glucoses now available to be chopped off. And our last enzyme, again works with enzyme 1, is phosphoglucomutase, which will convert our glucose 1-phosphate into glucose 6-phosphate, which we just saw in the previous 2 slides rather. It is central to all the metabolism that we have been talking about now. All right. So let's take a look at glycogen phosphorylase, and it's a dimer of 842 residues, and it catalyzes the rate controlling step in our glycogen breakdown, and it has regulation by allosteric interactions and covalent modifications. Our covalent modification here will be phosphorylation, and these regulators work differently with the enzyme if the enzyme's phosphorylated or if the enzyme is dephosphorylated. Our inhibitors for this enzyme are ATP, G6P, and glucose, and that should make perfect sense. Remember, what this enzyme's doing is it's taking your storage of glucose and chopping it up so it can be converted into something else, usually ATP. So if you have a lot of ATP around, if you have a lot of glucose 6-phosphate around already, or a lot of glucose, don't chop up your storage. Keep it as storage, so inhibit this enzyme. While if you're low in energy, which is AMP, if you have a lot of AMP around, this means you're low in energy, turn on this enzyme. We want to get energy, activate this enzyme. This enzyme uses a pyridoxal 5-phosphate or PLP cofactor, and it's only active if it has PLP bound. PLP is vitamin B5, and it's actually covalently linked to our enzyme via a shift base on lysine 680. Now, like I said, this enzyme has two different states. We're going to call them R and T state again. So T is inactive, R is active. And these states can be phosphorylated. Phosphorylation, we call it phosphorylase A. Unphosphorylated, we call it phosphorylase B. Now, AMP, when it's bound, will shift from T to R state. So we're looking at the left side here. When you have AMP bound to your enzyme, it's going to make the active form be more prevalent. While ATP or G6P will bind in the same place as EMP and do the reverse. It will force it into the T state. Now, you can actually phosphorylate this enzyme, and it has the same type of activation effects as AMP does. So when you phosphorylate this enzyme, you're attaching a phosphate group to serine 14. This will cause tertiary and quaternary structural changes, which will make the enzyme go in the R form. And the reason for this is that when you add the phosphate, the N-terminus will move aside, so your serine phosphate can interact with two arginine residues. And adding a phosphate group is basically the same thing as binding AMP. You're going from the T to R transition. So phosphorylase B, if you do not have any phosphate, you basically need AMP to activate it. While if you're phosphorylase A, you're already phosphorylated, you don't need AMP. It's just going to be activated by itself. So that's our first enzyme, and it will work chopping up our branches until we get to the situation where we only have 4 glucose molecules left. This is what we're calling a limit branch, and so we cannot chop off these molecules. And so that's a problem for us. And we have another enzyme called glycogen debranching enzyme. What glycogen debranching enzyme is going to do is it's going to take these 3 glucoses and break them off from our branch and add them to another chain. Now this chain is long enough that we can start chopping these glucoses off with our first enzyme that we just talked about. However, we have one sugar, one glucose that we cannot touch, even with our debranching enzyme. This is lost via hydrolysis and converted to glucose rather than glucose 1-phosphate. Now our debranching enzyme is slower than our previous phosphorylase reaction. So what happens is that if you're using your muscles, the phosphorylase will chop off all the branches extremely fast until it gets down to the last 4 residues. Moving these last 4 residues is extremely slow compared to our phosphorylase reaction. So this is why your muscles can sustain their maximum energy for only a few seconds, because all your glycogen is used up. Then you have to have the slow process of rearranging your branches before you can get more glucose out. So that's why we have maximum strength that can only last for like a few seconds before all of our glycogen is used up. And we have to start debranching it so we can get more of it. Alright, so our third enzyme is taking all the G1P that we made and converting it into glucose 6-phosphate, which we need for glycolysis. This is done by phosphoglucosamutase. And this is similar to a reaction catalyzed by phosphoglycerate mutase. So we just have a mutation reaction. So what's actually happening here is we have our enzyme, and our enzyme has a phosphate on serine. And we take our glucose 1-phosphate, and carbon 6 takes the phosphate from serine. Once we have that, we make glucose 1,6 bisphosphate. Remember, it's bisphosphate because we have two phosphates on different groups, not diphosphate. So our enzyme will then go and take our phosphate from our 1 position. So our enzyme is remade. Now we have glucose 6-phosphate ready to go. So remember, a mutase, all mutase is doing is that it's moving around these functional groups. And so it's not the same functional groups that's been moving, rather it's just kind of a swap. You take my phosphate, I take your phosphate, we're ready to go. So G6P that is produced by this glycogen breakdown can continue along glycolysis or the pentose phosphate pathway, as we saw in the image at the very beginning of this slide. Now, in the liver, when you break down glycogen, you can use this G6P and give it to other tissues. However, there is a problem. G6P can't actually leave the cell. So we need to first remake it into glucose. And the enzyme that's going to do this is glucose 6-phosphatase. Glucose 6-phosphatase will take this phosphate and just chop it off. So you lose some energy by doing this because you're not really using this phosphate for anything. But it is allowing our glucose to leave the cell. So this enzyme, this glucose 6-phosphatase, is in the endoplasmic reticulum. However, G6P is produced in the cytosol. So before G6P can leave the liver, it has to go to the ER via an enzyme called G6P translocase. Then it can be hydrolyzed. And once hydrolyzed, your glucose and phosphate are returned to the cytosol via specific transport proteins, and then it can be sent along your body to be used. And if any one of these enzymes don't work properly, you will have what's called type 1 glycogen storage disease. So any one of these things go wrong, you cannot break down glycogen, you cannot send it to the rest of your body from your liver, and that can have some health consequences. So that is that for glycogen breaking down, and I will see you in the next video.